السلام عليكم ورحمة الله وبركاته. I'm going to share my screen. Oh, the previous one. All right, we'll finish with this example, then we'll move on to the next chapter. As you may recall, we have started looking at this problem in our last class before the time was up. We have a block of wood, square cross section and length 60 centimeter, and whose weight is 318 Newton. The question is, will the block float with sides vertical as shown? Okay, so here we are going to apply the force equilibrium to find the depth of submergence, then determine if the block is stable above the long axis by applying the equation by calculating the GM. Okay, and then if it is stable, fine. If it is not, we will repeat. We will tilt the block and then change GM to see if we will have a positive value. As it will be positive only when GM is positive. Okay. And GM is the distance between the center of gravity and the metacentre. Okay. And there, the first thing we did, like explain, is to find the depth of submergence, which is D, which is the distance to which the block has been submerged. Okay. In water, or yeah, in water. And to do that, we use the fact that F is equal to summation of forces in the vertical direction is 0, equilibrium equation. From here we have the weight and we have the buoyant force, which is simply MIVD, volume of the submerged area. Okay, volume of the submerged block. Volume of the submerged block, which will be D times the length times the width, which is 30. Okay, so here we found D, 18 centimeters. Now, to test the stability, we evaluate GM. I mentioned before, if GM is greater than 1, that is positive. Okay, then our body is stable. And conversely, if GM is less than 1, which implies it is negative, so it should be greater than 0, not 1. Greater than 0, because anything greater than 0 is positive. It can be 0.5. 0.5 is still positive. Okay, so the actual thing I should be using is not 1 but 0. Anything greater than 0 is positive, anything less than 0 is negative. Okay, so if is less than 0, that is negative, we have the body to be unstable. It is unstable. And yeah, this is GM, determine the moment of inertia from the water line, which is BD cubed over 12. Okay, the formula is there, BD cubed over 12. Okay. E from statics, chapter 10, I think the last chapter. We have the moment of inertia for a rectangular section to be BD cubed over 12. This is exactly what we have here. Okay. Okay. Breadth is 60 and the depth of the section is 30. Okay. Then V here, like I mentioned before, is the displaced volume. V is the VD, the displaced volume. And the displaced volume is found by the volume submerged, okay, which is here we use P, which we found here, okay. Then this one, which is CG. CG, C is the center of buoyancy, and G is the center of gravity. Center of buoyancy, as we explained before, is the centroid of the displaced volume. So here, this is the displaced volume, displaced section area. So the centroid of this a rectangle will be here. It will be at D over 2. Okay, the centroid will be at D over 2. Then the centroid of the block, the center of gravity of the block is somewhere here. D is 18, right? D is 18, so the center of gravity will be less than D, somewhere here. Okay, which is at 15, at 30 over 2, at exactly 30 over 2, which is 15. Okay, this is G, center of gravity, which is 15 here, and this is C, which is the center of buoyancy, which is at a distance D over 2, D over 2, which is 9. Okay, so from here to here is 15. What will be the distance from C to G now? This one is going to be 15 minus 9. So that's why we have 15 minus 9. Then when we substitute everything here, here we have at the outer line, if you remember, G, I, I is the moment of inertia of the horizontal section of the floating body at the free surface of water about a longitudinal axis. Okay, horizontal section of the floating body at the free surface. So I here is at the free surface here, at this surface. Okay, so the section is going to be regular, this 30 and this 160. Okay, so that's why we have BD cubed over 12. Okay, we didn't use the depth, either submerged depth or the total depth of wood. Okay, it is at the water section. Okay, at the submerged, it is at the water surface section. So GM now turned out to be negative, minus 1.83, which implies body is unstable. So we move to the next. We have to change the configuration, re-evaluate them, and see if it will be positive. We need to hit 1 and 2. Apply force equilibrium to find the depth of submergence, and then determine the block, determine if the block is stable for the long axis. Now, because the metacentric height is negative, the block is not stable about the longitudinal axis. Thus, a slight disturbance will make it tip to the orientation shown below. Okay, if it is unstable, it doesn't mean it is not in equilibrium. It is in equilibrium, but the slightest disturbance will now unsettle, will now change the equilibrium, or will now make the body not to be in equilibrium anymore. Okay. So a slight disturbance will make it tip to the orientation shown below. Okay. Note that calculations to find dimensions, this one and this one, are not shown. So the same body here, when you now push it, let's say rotational disturbance, when you apply, you rotate it, okay, it will shift. Okay. Now let's evaluate the new configuration. Center of gravity will change the positions of the center of buoyancy, and then we apply the same equilibrium position, equilibrium equation. When it is tilted, we have the width here, which we need to find out. Okay. I have the depth. This is the center of buoyancy, which is C. Okay. This is the center of gravity, which is G. Okay. We need to make some calculations here. Find W. Okay. So the first thing we do here is to find W. And then from there, we can find the new positions of the center of gravity and the center of buoyancy. Equilibrium in the vertical direction still, because it is floating, so we still have buoyant force balancing the weight of the body, which makes summation Fy equals 0. Okay. So we still have the weight. This is the unit weight of water. This is the volume. So this is the volume, the new volume now, which is different from this one, which is different from this volume now. Okay. It's different from this volume. Now to find W, displaced volume is equal to the block volume minus volume above the water line. Okay, the displaced volume, which is volume below the water line, is going to be the total volume of the block minus the volume above the water line, which is this volume. Okay, so that will give us the remaining volume. Okay, and don't forget, we already have the displaced volume, which we found here. Okay, so now the block volume, we know the block volume based on the dimensions of the block, that's the total volume of the block, minus the volume above the water line. If you look at this, to find the volume above the water line, this is like an isosceles triangle. You must have learned the different types of triangles. Okay, isosceles triangle is one in which two sides are equal. Okay, and when you have line here, if this is W, then this will be, okay, let me bring it here, bring it out. This is approximately isosceles triangle having two sides to be equal. This side is equal to this side, and this angle is equal to that angle. Okay, when you bisect isosceles triangle, this will total is W, so this is now W over 2, and this is now W over 2. Okay? And this is now W over 2, and this is now W over 2, and it gives you another isosceles triangle. Okay, because this is also now W over 2. Okay, so now to find the area of this is going to be half base times height, area of a triangle. And hear me talking slowly. Since yesterday I wasn't feeling fine, so I'm trying to see how much we can cover today. Okay, definitely I'm planning on Sunday I will make a makeup class. I will announce the time. Anyone available should join me. Okay, remember we have some lectures to we have some makeup classes which we haven't done. Okay, so bear with me, taking it slowly. Okay, because not really since yesterday I not feeling so fine. Okay, so now the area here, area of a triangle is half base times height. Okay, in this case the base is W. Okay, the base is W, which is here, and the height is W over 2. Okay, so this you have W squared over 4. That's the area. So the cross-sectional area times the length. The length is 60 centimeter, which is 0.6. So that's why you have this term here, W squared over 4. Okay, W squared over 4 is the area, and then the length is 0.6. From here, you can find W. So W is obtained to be 0.379, which is 37.9. I had some sound. Let me see what you are writing. Today we have full class. Good. Okay, so now having obtained W, to find this one, I will do this one. That is the distance between the centroid, the center of gravity, the top of the water, then I will leave this one for you to do. Okay. Now, to find the new CG, okay, the center of gravity, okay, distance to the top of the line, okay. The center of gravity remains at the centroid, okay, remains at the centroid. Okay. Remember the sides to be the side of the block to be 30 centimeter. This is 30, 30, 30, 30. Okay. So what will be this length? Hypotenuse. Use Pythagoras theorem. Yeah, to find the length. Okay, the vertical line. Okay. Use Pythagoras theorem, which is square root of 30 squared plus 30 squared. Okay. Let me get my calculator. It will be about 42.4. Okay. 42.4 centimeter. And the center of gravity will be at the center. Okay. So over 2 from here to here now. It's now going to be 42.4 over 2, which is 21.2. Okay. So this is 21.2 centimeter. Okay. This is 21.2 centimeter. Okay. And then we know that from here to here, based on this figure, is W over 2, isn't it? Based on this isosceles triangle. From here to here is W over 2. And W is equal to this, so W over 2 is going to be 37.9 over 2, which is 18.95. 18.95 centimeter. Okay, so this is 18.5 centimeter. So now, what is now the remaining distance? Because the total distance is what we found here, okay, which is 42.4. 42.4 centimeter. So now, what is now this distance? That is, this is distance between G to the top of the water. So the distance is simply going to be 42.4 minus 18.95 minus 21.2, which will approximately be equal to 2.26 centimeter. Okay, so this is how it is obtained. This is just geometry. There is nothing, it's just simple geometry. Okay, and then, like I said, I will leave the remaining, that is to find this one now, 5.73. Okay, which is now the distance from the centroid, from the center of gravity to the new center of buoyancy. So the center of buoyancy is going to change now. It's no longer here because the shape of the displaced volume has changed. Okay, so there'll be new center of buoyancy. Okay, so now you find this center and then you find this distance. Okay, I did for G, you do for C. Okay, so now moment of inertia, remember, is the cross-sectional section of the immersed volume, okay, at the water interface. Okay, so it's going to be W here, okay, and then times the length, because that is the cross section at the interface. So it's still BH cubed over 12. E is going to be length, and W is going to be H. So that's why you have, this is now W, which is what we found here. Okay? So this is the new moment of inertia. And then we go back to substitute. This is our new CG. Okay, what is the distance between the center of buoyancy to the center of gravity? And then this is our new displaced volume. For the displaced volume, substituted here. Okay, this was our displaced volume before. Okay, and this is the new displaced volume. Then when we substitute, we find GM to be 0.027 meter, which is positive because it's greater than 0. So because the metacentric height is positive, the block will be stable in this position. Okay. So this is an exercise for you to try. You need to really work, solve some problems to really understand these concepts very well. Okay. It's an exercise. You can try and do it. A cylinder. Okay. This determine the metacentric height and the state the condition of its equilibrium. Again, I also downloaded another document here with some good solved problems. Okay, the document contains, solved problems under the stability. Share that. Stop sharing this one. So this is the document. It contains good other examples on the stability and the application of the formula. Okay, so take your time to follow the examples and understand them carefully. Okay? I will upload it on Blackboard after the class. This is it. It will give you good grasp, give good understanding of the concept. Okay? Like I told you, because of what I am currently feeling, I'm supposed to start the next chapter, which is chapter 4. I have the slides to start with. It's about fluid kinematics. We are done with fluid statics. Now we'll move to fluid kinematics. Okay, which will be dealing or describing the motion of fluids without necessarily considering the forces and moments that cause the motion. Okay, but sincerely speaking, I am not feeling fine, but I promise you, inshallah, on Sunday we are going to have we will have a makeup class, okay, in which we will continue from here on chapter 4. Okay, So I will announce the time. Most likely maybe in the afternoon. Okay. And then we'll see what happens. Okay. Any question on what we discussed so far? All right. Absence of any question, we call it a day. Thank you.